This is Iris Berryhill's Calc 2 final presentation. I got the idea for this presentation over a year ago. I was in physics, AP Physics 1, and I was like, it was algebra based, it was not calculus based. But there's some stuff that kind of connects to calculus. The area under a velocity curve is a function's displacement. The area under a curve is a function's integral. So we only ever worked with constant acceleration. That was the highest we would take it. We didn't talk about an acceleration that was curved or linear, only constant acceleration. Because that's hard to do without looking at physics. That gets really complicated. But I'm gonna take you through a function where acceleration is not gonna end up being constant later in a moment. So the foreshadowing. Okay, so we start with a velocity function. Let's take the derivative of this velocity function with respect to t. That's going to equal 2t plus 2, which is the acceleration. Connecting back to physics, if we had a velocity function, let's say the velocity function was 2t plus 2, we would know the acceleration was 2 because that would be the slope of the velocity curve. But this is the slope of this velocity curve, this acceleration is. And we can only, we can't look at this and be like, what's the slope of that? Because it changes. I will graph it, but I will graph it. It looks like this. Starts at 1. Starts at y equals 1. It grows. It grows. Yeah. But then I was like, so what's a limitation of this? Because I could take the derivative of acceleration, I could find jerk, and that would be 2. Jerk is 2, and I could take the derivative of jerk and find that there is no snap, crackle, or pop, which we didn't even look at in physics 1 because that is complicated. But if I take the integral of this acceleration, 2t plus 2, dt is going to equal t squared plus 2t plus c equals velocity. Is that my velocity? How do I get back to the 1? Where'd the 1 go? This is a function for change in velocity. The area under the curve is the change in velocity. That was mind-blowing to figure that out after, over a year after all these other people had this aha moment. I was like, oh my gosh. Sorry if I sound like this is like my 17th take. I've been looking at like the same, I've had this function for hours. I've looked at this so many times, but it took me a minute to figure out what I wanted to do with this part. I think I better have it down. So with that, I found that I can't really get the instantaneous velocity from acceleration because I'm going backwards without finding more variables, and there the kinematic equations really come into help, really get to be helpful. Yeah. But here we have a racetrack, and say it's a car, it's going around, so it has to accelerate, decelerate, whatever, and it's trying to get around as fast as possible. So it's going to take six turns, let's say, right? I've mapped out its displacement versus time, or distance traveled versus time. the graph of that function is going to take 6 turns. That's what's going to happen, I think. So it should be to the seventh power. So what this is going to give me is if I graph d versus t, I have a function with 7 turns. So a graph of displacement versus time gives me, I'm going to make something up, x to the 7th plus 2x to the 6th plus 3x to the 5th plus x to the 4th plus 2x to the 3rd plus x squared plus x plus 0, because we start from rest. And this is super, just making this up. So what's the velocity as a function of time of this function? Well, we can take the derivative of this, plus 12x to the 5th plus 15x to the 4th plus 4x to the 3rd plus 6x squared plus 2x plus 1. And what's the acceleration as a function of time? What's 7 times 6? 36 plus 6 is 42. 42x to the 5th plus 12 times 5 is 50. 62. 62x to the 4th plus 60x to the 3rd plus 12x squared plus 12x plus 2. Well, what's jerk as a function of time? We can keep going. Calculus, I guess, calculus ends up being really useful for modeling the motion of an object that takes a lot of turns. If I go on the highway and I have, like, I create a graph of every time I speed up or slow down, or sorry, no, not that. I'm brain fogged. I've been, yeah. But if I take readings, I just thought of this. I start my watch, right? And I have it tracking my distance traveled. And let's say it's actually really great and it's every step I take is like the same distance and it's perfect and it knows exactly how far I've actually gone over time, right? It can plot, right? It can take 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and it can say you took a step in the first second, 5 steps in the second second. I didn't, but you can say that. We can create a graph of my distance traveled versus time. And we can also create a function to model that graph approximately. And from that graph of position versus time, we can get my velocity versus time. We can get my acceleration versus time. We can get all these things from just knowing where I am and at what time. We can model how fast I'm talking. We can model how fast anything's going from just this, and we can take it down so many levels. And that's what I'm saying. So my outro. My outro is I had a lot of misconceptions about what I was gonna find. First off, I thought that my first thing was I thought that the derivative of acceleration is going to give me velocity. The derivative of velocity gives me acceleration. That was my first thing. My big thing, though, was I thought I was going to get, like, instantaneous velocity from an acceleration function. But it turns out I'm not. I'm going to get my change in velocity, and I can take the change in velocity over a very small interval. And I can graph my change in velocity. What am I saying? But yeah, I'm going to get change in velocity. I'm not going to get velocity. I can't get velocity from just taking an integral. I need to do something more. I need to use kinematics, or I need to pull something else out of my head. But I can get acceleration from just velocity. And if I start with time versus distance readings, I can get anything. And that's the point.